The storage industry has been wrestling to incorporate persistent memory in system and software designs, but even bigger challenges lurk around the corner. Computing systems include a lot of other memory besides the system main memory, DIMMs. The near future will bring persistent caches and even persistent registers to processor chips. This move to persistence will allow properly tuned software to perform better and will reduce power consumption. But the same capability could undermine security and reliability if not carefully applied. I'm Jim Handy.
And I'm Tom Coughlin.
We're the co-authors of a new report that examines emerging memory technologies and forecasts the adoption of these technologies and their impact on computing. First, a little bit about who we are. I am an industry analyst covering the memory business, semiconductor memory business, and SSDs after having worked in the semiconductor industry for a number of years. And Tom?
I'm Tom Coughlin, and I'm a president of Coughlin Associates. I do consulting, but I also do analysis of storage technologies and their trends. I've been working in this in storage for about 39 years, and my interests include emerging memories, and that's what led Jim and I to work together on a report, which will be the basis of much of our presentation here.
Thanks, Tom. In this presentation, we will explore how new, emerging, persistent memory technologies will naturally become a part of all computing architectures, displacing NOR flash on MCUs and the SRAM and server processors. And then we'll discuss the implications of this change to software and hardware designs. Let's get started. There are 5 parts of our presentation. First, we'll discuss persistence and its history in computer design. Next, we'll lay out the reasons that the memories within server processors, the cache memory, and even the processor registers will naturally become persistent. Third, we'll discuss the implications this change will have on systems. Fourth, we'll look at the benefits to some common applications. Finally, we'll summarize and take questions from the audience. So let's talk about the first of these, the history of persistent memory in computers. This is a conceptual chart of the memory storage hierarchy in computing applications today. Most of you have probably seen it before. The chart represents computing's memory storage hierarchy. For a memory or storage technology to make sense in this hierarchy, it must be cheaper than the next faster technology, as measured on the horizontal axis, and faster than the next cheaper technology, measured on the vertical axis. Intel has inserted its Optane DIMMs, also known as 3D cross-point memory, or officially now dubbed the Optane DC Persistent Memory Module, to fit between DRAM and NAND flash SSDs. The technology has the correct speed to do this and has been wrestling to get its cost to the point where it works in the chart and is also profitable for Intel. Everything in this chart from 3D crosspoint down to tape is persistent. Everything from DRAM up is volatile. It loses its data when power is removed. The memory hierarchy wasn't always like this, though. Let's go back 60 years. This is the same chart as it would appear in 1960. Note that there are only 3 tiers in the memory hierarchy: core memory, hard drive, and tape. In those days, the tape could have been either paper tape or mag tape. The HDD may have been a magnetic drum instead. Cache hadn't even been invented yet. The most interesting thing about this chart, though, is that everything on it is persistent. Even the memory was persistent. This wasn't really appreciated at the time, though. Some operators trusted that the core memory, as shown in this slide, would retain its data when they shut off the power. These operators booted their systems pretty fast, since all they did was to turn the power back on. Others were less trusting and would boot up the system every time they powered up, reloading all of the software from the HDD or tape system. At that time, people didn't think so much about persisting data as they thought about storing it. It would be stored on HDD or tape. When the core memory was replaced first by SRAM and then by DRAM, programmers weren't too concerned since they had not developed a code base that depended on storing data in memory. This is very different from today, where enormous attention is being devoted to persisting data within the memory to improve performance. So that's where we came from. Now let's talk about where we're going. Persistent caches are inevitable. Certain very real forces in chip design will require processors to migrate to persistent memory as a replacement for the SRAM currently used in caches. It all has to do with certain technologies that have hit a limit and have stopped scaling. Let's look at them. Semiconductor process shrinks have worked for decades to reduce costs, as is illustrated in this chart. In this case, the process runs along the bottom, shrinking as we move to the right. Relative cost on the vertical axis has historically come down with every process shrink. But flash memory has a problem. Flash is unable to scale past a certain point. For NAND flash, this was 15 nanometers, so 3D NAND was adopted. NOR flash, the only non-volatile memory currently used to store the code in microcontrollers, ASICs, and other systems on a chip or SoCs, is unable to scale at all past 28 nanometers. Its cost declines, indicated by the red line, cease at this point. To address these issues, manufacturers are migrating to new memory technologies. Emerging memories are needed to allow further cost reductions. These emerging memory technologies are represented by the black line in the chart. Today, they're more costly than NOR flash, but they will eventually cost less than flash to produce, since they can scale past 28 nanometers. Tom Coughlin will walk you through the emerging memory types and their benefits.
Thank you, Jim. There are many emerging memory types vying to replace NOR flash. All share similar attributes. They all have a small, single-element bit cell that promises to scale smaller than current technologies to support small, inexpensive die and 3D stacking. They also promise to be easier to use than flash memory by supporting write-in-place with no need for a block erase, and they have more symmetrical read and write speeds. Finally, they are all non-volatile or persistent. Data doesn't disappear when power is turned off. They can all be used as persistent memory. New memories are necessary for Moore's law scaling to continue. The technologies we're talking about include ferroelectric random access memory, magnetic random access memory, that's MRAM, resistive random access memory, RRAM, and phase change, or PCM memory, such as Intel and Micron's 3D crosspoint, otherwise known by Intel as Optane memory. Even SRAM is scaling poorly. This chart plots the cell area for SRAM cells that have been presented at recent IEEE conferences in the last few years. Although the cell size, the vertical axis, has been shrinking to keep pace with the process geometry that's running along the horizontal axis, it suddenly stops shrinking as the process transitioned from 22 to 14 nanometers. To show what this means to chip sizes and costs, I will present an animated graphic. This is a photograph of an Intel processor chip made on a 45 nanometer process. You can see two very different parts of this layout. The less regular part of the chip at the top is the logic, and the lower half, with its very regular patterns, is the SRAM used for the on-chip caches. In the past, the entire chip would scale with process shrinks, as is illustrated here. As processes moved from node to node, from 45 to 32 to 22, and finally 14 nanometer, the die's area and cost would be half that of the prior generation. This follows a very nice scaling curve. This assumes that the SRAM keeps pace with the process geometry in terms of shrinking die area. And the prior slide showed us that this didn't happen at the 14 nanometer node. We'll use the same chip again. Keeping in mind that the top half is logic, which will scale in proportion to the process, and the bottom half is SRAM, which will scale less aggressively. You can see in this series that the top half of the chip gets pretty small towards the end, and but it only accounts for about 20% of the total die area at the smallest process node. Yet the SRAM doesn't scale. This results in a pretty large chip. In fact, the die size trend starts to level off at the end. This black line only indicates the height. The area of the chip is roughly equivalent to the square of this figure, or the area of this figure, indicating a very significant difference between the two, the total shrink and the delayed shrink diagrams. The SRAM is causing the chip to be larger and more expensive. A maturing memory, were it readily available, then this SRAM would have already been replaced, and we wouldn't be calling it out as a concern for future chips. Microcontrollers, ASICs, and other SoCs will do a lot of the groundwork for this change. Their need for a NOR replacement has already driven major foundries such as TSMC, Samsung, Global Foundries, and many others to develop emerging memory technologies, mainly MRAM and resistive RAM, to replace a stalled NOR flash technology. These foundries will drive the cost out of these new technologies, rendering them attractive not only for NOR flash replacement, but also as a replacement for SRAM. First, slower SRAM, and then the fast SRAM in upper level caches. When this happens, persistence will follow. Not only participating in the 3D crosspoint and below technologies, but now becoming an important part of the upper half of this diagram, the different levels of cache memory. I'll pass the baton back to Jim, who will explain how persistence will impact systems.
Thanks, Tom. The move to persistent caches will have a profound impact on systems, not only on how they perform, but also on how they are configured to take advantage of these changes. As an example, SNIA has been working for the past 7 years on the NVM programming model. This well-conceived approach provides a consistent, unified means for application programs to operate in an environment that includes both persistent memory and more conventional memory and storage. Old applications can perform in this environment without change, and new applications can be developed to tap into all that persistent memory has to offer. It took a lot of work to get this far, but things have only just begun. Other parts of the system must be updated to adapt to persistence. For one thing, all of those persistent memories we showed you a few slides ago share two unfortunate attributes. They are slower than DRAM, and they have faster reads than writes. DRAM buses, or memory channels, have been developed over time to run at a fixed speed. The various forms of DDR don't easily accommodate a non-deterministic, non-uniform combination of fast and slow memories. To accommodate the speed changes stemming from 3D crosspoint memory, Intel had to develop a proprietary spin on the DDR4 bus that the company calls DDRT. Over time, this is likely to change to the new CXL bus. The more complex memory channel required for the development of a memory management unit, an MMU, that could deal with the various kinds of memory attached to the memory channel. One issue with this is that variations in time for writes could have been accommodated through the use of interrupts, but interrupts cause context switches, and context switches are slow. The next slide will elaborate on that. Meanwhile, very little of today's application software understands persistence. The real power of persistence will only be felt once applications avail themselves of the benefits of persistence. A lot of this depends on standards, and organizations like SNIA, JEDEC, and others are busily working to make all of this happen. This chart details the context switch problem. 4 devices are shown: HDD, SATA SSD, NVMe SSD, and persistent memory. The access latency for each of these is shown on the vertical axis in nanoseconds. HDD is about 100 milliseconds. SATA SSD is about 100 microseconds, and an NVMe SSD is about 10. The best way to deal with these latencies is to issue a command and then to interrupt the processor when the device responds, causing a context switch. A context switch is a slow process, though, as registers are pushed onto a stack and new data is loaded. At a latency somewhere around 1 microsecond, it becomes unclear that an interrupt is the best way to deal with a slow device. And at latencies of around 100 nanoseconds, it is clearly faster to put the processor into an idle loop, polling the device to wait until the operation is done. This is the zone where 3D cross-point memory now resides. Over time, a better approach will be devised, but for the time being, 3D cross-point memory is polled. Tom will now walk you through the power and performance improvements that should result from the use of persistent caches.
Thank you, Jim. The move to persistent caches will have a profound impact on systems, not only in how they perform, but also in how they are configured to take advantage of these changes. There are significant benefits to persistence, despite all of the support requirements. Persistent systems consume much less energy. They can be powered down for a greater share of their time. Persistent caches accelerate transactions. Transactions are posted as soon as they are calculated. These capabilities provide significant value for data center and embedded system applications. To underscore how greatly persistent memory and even SSDs can reduce system energy consumption, we look to a study from Carnegie Mellon University, Penn State University, Intel, and AMD. This study compares the energy consumed for 6 programs listed in the chart on 3 types of system. One system is based on hard disk drive, one is based on SSDs, and one that uses persistent memory for storage. While the study breaks the numbers down in much greater detail than shown here, the findings are compelling even at this higher level. For example, grep-R, the program that had the lowest savings, used 35% less energy with an SSD than with a hard disk drive. And the move from SSD to persistent memory provided a 70% energy savings. That translates into an 80% savings over the hard disk drive system. Note that this is the program that was the least impacted. The more highly impacted programs, CP, Postmark, and the complex MySQL, had savings ranging from 89 to 99% over the hard disk drive-based system. Moving persistence to the cache is likely to provide even greater benefits, although today those benefits are not known. The same study compared the relative execution time for the same 6 programs listed in the chart on the same 3 types of systems. Again, the study breaks the numbers down in much greater detail than shown here. As before, even the speedup of the least impacted program is compelling. For grep-R, the SSD system took 44% less time than the hard disk drive system, and the persistent memory system took 62% shorter time than the SSD system, and 79% less time than the hard disk drive-based system. The 4 programs with the greatest benefit, CP, Postmark, and both versions of MySQL, had savings ranging from 94 to 99% over a hard disk drive-based system. As before, the industry can expect additional benefits through the use of persistent cache memory. And this leaves us advantages for data centers. Power consumption is perhaps the most difficult issue facing hyperscale data centers. Use of non-volatile cache can result in less data movement, leading to faster processing and lower power consumption. Some modern data centers are being built near intermittent, low-cost power sources, such as wind farms, to run complex but non-time critical operations. These data centers may be pausable, stopping processing when the wind power drops. Using non-volatile caches will allow faster recovery of operations when the power resumes. Replacing volatile caches with non-volatile memory will enable faster recovery when there is a power loss in a conventional data center. This can also reduce the need for backup data center power. In the case of embedded electronics, high-end embedded systems use processors with internal cache memories. Such systems include cell phones, autonomous vehicles, and high-end instrumentation, such as the MRI scanner pictured here. For energy-constrained systems running on batteries or harvested power, the energy savings of frequent power-down modes using persistent cache memory could multiply battery life. Since MRAM and RRAM scale better than SRAM, a given size chip die can have more MRAM or resistive RAM than SRAM. More non-volatile memory can store more data and thus lead to fewer cache misses and subsequently fewer slow accesses to external memory. These activities improve performance and also saves the energy of moving the data around. Applications such as AI inference, often done at the application endpoint, can require significant cache memory. Using MRAM or resistive RAM, more memory is available in a given die area, allowing smaller die for the system on chip and thus lower die cost. The issues caused by persistent memory and many more have been dealt with in the case of persistent main memory. But now the process must begin again to support persistent caches. Although we didn't mention it, the first support that was provided for persistent memory was from the BIOS, so that persistent memory-based systems could boot, knowing that they didn't need to reload memory. Then came operating system support, thanks to the SNIA NVM programming model. The programming model is supporting today's ongoing effort to develop application program support. Standards must be developed to allow the entire ecosystem of applications to develop in order to support persistent caches. Finally, there will need to be hardware support to accommodate the use of persistence at all levels of the memory and storage hierarchy. And it doesn't stop there. After persistent cache comes persistent registers. And with this, the process begins again. Much of the information in this presentation was drawn from a newly released report on emerging memories that Jim and I co-authored. The report that this data comes from is available online. It describes the entire emerging memory ecosystem, the technologies such as phase change memory, resistive RAM, MRAM, ferroelectric RAM, etc., the companies that are engaged in these activities, the markets that they will be used in, and the support requirements in order to enable them to happen. We provide forecasts examining emerging memory consumption, both for the embedded emerging memories and for discrete emerging memories. This report is 201 pages long with 31 tables and 142 figures. You can visit the URLs at the bottom of this slide in order to learn more. So what does all of this mean? What do you need to do to remain prepared for this important shift in memory technology? The message is simple. Persistent caches are on the way. Persistent registers will follow. All of this persistence will require a lot of support. It's not too soon to start considering how to handle this from the perspective of operating system support, BIOS support, hardware support, and application changes to take advantage of this enormous windfall. And finally, if you want to gain a real understanding, it's important to buy our report. So with that, I'd like to thank you, and we'd love to get feedback on this session, and we'll take questions